I believe after number 62, problems like this showed up. Was 63 assigned?
Yes.
Okay. 63 started this concept, started this idea. Where they're trying to bring a lot of different things together, but all underneath the umbrella of continuity. If you guys haven't noticed yet, chapter 1 is limits and continuity. So, why might this not be continuous? Thinking of all that we did yesterday, discussing continuity with my phone and the webcam and whatever. We did it. And the notes saved online are from period 6 when the computer got working again, actually got working by period 2. And there's a video online also. They got this example done, we didn't, we're catching up. For once. It's backwards, but keep going. Took my entire computer shutting down for you guys to fall behind. Why might this not be continuous? Where might it not be continuous? Yes. Because, isn't this a quadratic? This piece, for all x values below -1 or to the left of -1. Would a polynomial ever have a discontinuity naturally? No. How about this polynomial? He's a quadratic even though there's an a. Would he have any discontinuities naturally? No. So the only way this could be continuous is if these, what? If they come together in a way that they don't connect, right? So then if they say to make this continuous, then we need to think of both of these pieces and how to make them come together. Now, I could just give you the answer, but that would be no fun. I could just give you the way, but that would be no fun. The easy kid, if they were tutoring you, would just say something like, well, just do this and this and this, and then you have the answer. But can we think through the concept really quickly? Definition of continuous is up there. Definition of continuous is, ooh, look, the forever sign up there. What do I need to be true? Them to connect. That's the idea. I need the pieces to connect. But mathematically, how do I do that? What equals? Don't say they. Pause. AP language, we can't be ambiguous. Okay. On the free response, no, this was just a good life lesson. AP lesson. If we're doing like a free response, which is like a long answer question on the AP test, like DBQs and all that sort of stuff. Like a free response is like you're actually working out, showing your work, showing an explanation. If you say the word it or the word they, and it refers to something that it shouldn't, or it doesn't actually have like a noun that it refers to, they will not give you the point. They will not give you the credit. That's just like a warning. It's really easy to say it or they and not actually have a full comprehension, and the AP graders would know that, or would know that your answer is not complete and take points off accordingly. So I'm picking on Adam, but it's like a broader truth we need to think about. So, what did you mean by equal? Ooh. I like what he's saying, but you have to tweak it a little bit better. He said the functions need to be equal. Why is he saying functions? Because technically there's only one function, right? There you go. How about the parts of the piece y need to be equal? Where? Their y values? Yeah. For? Got it. So I need the two pieces to be coming together towards, wait a minute, towards. I need them to be coming together towards, isn't that a limit? Wait a minute, I'm just doing a big old box, aren't I? Can't I just say the limit as x approaches -1 from below? Which piece do I naturally, will this be referring to? Or am I referring to? The top piece. So to find this limit, wouldn't we plug into 4 minus x squared? You guys agree? But I can't just consider from below or the top piece. That's mathematically how I can consider the top piece. At -1 because it's not technically at, so instead I come towards. But I'm plugging in. But I also need to consider coming from above, and which piece would I be considering then? The second piece, which would be a times, not x squared, because I plug in, right? So technically for a function to be continuous, I need the below to equal the above to equal the function at. But guys, this at is totally fine, because where is this at? At, where's the point, where's the value? Which piece? 1 to a piecewise function, right? It's not below, it's not above, oh, but it is or equal to. So it'd just be the exact same thing as this one, so that's kind of boring. Okay, whatever. So these two are already equal, so that's a for sure thing. And these two, what do they tell me to do? Make it continuous. Well, if it's continuous, isn't this a true statement? The limit as I come from below has to equal the limit as I come from above has to equal the value at. So therefore, those two are already true just because they're the same piece. These two need to be true. Do you see the math? You cheese it at this point because now I have 4 minus 1 is going to be 3, and then I have a times 1 squared is a plus 1. What must a equal? What does a equal to make this function continuous? You have the definition of continuous, which was your foundation that you built off of, which made you consider each and every piece. It made you think about what must be true to make them equal, or to make the values connect. So if I was to actually graph this, which there's no purpose for you to unless you're a very visual learner, I would have a quadratic that's been shifted up 4, a downwards facing quadratic, although he's less than -1, so actually he's not here. Instead, he's going to be, where was it, 4 minus 1, he's at 3. -1, he's at 3. There you go. And then the other guy was x squared plus 1, which now that we have the 2 plugged in, we could actually get some values if we really wanted to, like this guy is going to be here-ish, I believe. But we had to get the right parabola that would connect perfectly at -1. And if he was anywhere else, if that A was anything different, it would not have actually connected, so it would not be continuous, because it would be one of those broken dudes. So do you see how I use the definition of continuous? Then I basically did what Adam was saying, which was a good catch of I need these two pieces to connect, so I need their values to equal, but all of that was because we can take limits from below and from above. So, oops, I switched them. Let's see how much you understand it, because I have, let's do one more. I have another example. Go. This is exciting, because guess what? You're not just missing one variable, you're actually missing 2. Talk it out in your groups. You need it to be continuous everywhere. Okay, groups, collaborate. Just talk it out. This isn't a quiz. This isn't a test. You don't have to do it by yourself. You just watched me go through one, heard a little bit of explanation from Adam and I. John's idea is explain what you're doing with a mathematical reason. What?
I did not. That is a plus.
Continuous everywhere. These are going to be totally fine, except for maybe. Quadratic, linear, cubic. All polynomials, all continuous everywhere, except for possibly. Yeah, 2. That could be a problem. When they come together, they can be broken, or -1. So now we have 2 possible problem areas that we have to address, and we need to make sure in both of those possible problem areas that this function is fluid, is continuous, flows one piece right into the other. So how did you do it? How did you do it? I'm not even asking for the mathematical explanation as far as the definition of continuous and how it ties in and why. I'm not asking the why, just the how. What's the first thing a group did? You guys were discussing. So if someone's quieter in your group and they knew what they were doing, you voiced their ideas for them. What's the first thing you did? Limit above 2? Okay. So limit above 2, limit as x approaches. We already did the definition of continuous. Madison, that has you plug it in where? Good. Okay. I could know where this piece is headed, even though it's going to have a hole there, by taking the limit and just plug it and chug it. But what do I need that to match up with? The other 2. Cool. So that would be the limit technically. This one's going to be above because it's greater than. This one would be the limit from below, right? To plug into the other piece, and you set those equal if it's continuous. So m times 2 plus 1. You guys saw that wasn't enough, right? I have one equation with 2 unknowns that's algebraically impossible. I can state one in terms of the other. Like a relationship, like an equation, but I can't solve. So I need the other. Exactly, because I have 2 problem areas. I had where it connects at 2 or where it comes together at 2, hopefully coming together. But also where the x values come together at -1. So then, all right, this group has helped, this group has helped. Someone else, any group 1, 4, 5, or 6. Who wants to pitch in? Kyle just got back. We'll give him a little bit of grace. Kathleen, what do you guys plug in? Plug in 2? I just didn't hear you. Sorry. We're just saying that you did all. Oh, this one? Except, what am I changing? Approaching from below and above, but what value? Oh, yeah. Right? So coming from below -1 and coming from above -1. So that's it equal up as well. So from below -1, what piece am I plugging into? The bottom one. True, less than or equal to. So that's going to be 2 times -1 cubed. Plus -1 plus 7. I need that to equal from above would be the other piece, right? -1 plus. Ooh, I love it when I get zeros in equations. It makes my life easier. Anybody remember partial fractions last year?
Yeah.
And how we were plugging in zeros to try to get rid of some variables to solve for other variables, the capital A's and capital B's and capital C's. Anyway, why am I saying that? Because -1 plus 1 ends up being?
Equal.
Nice. So let's take these little pieces, these little algebraic expressions, and let's solve. So this guy I end up with 4 plus 5 is 9. 9 equals 3n plus k, right? And this guy I end up with 4? 4 is equal to the 0, gets rid of the m, equal to k. I already have 1. So you guys just think algebra and systems of equations, can't I go plugging in and they end up with? I have a 4, take it away, I have a 5, I have a 5 divided by 3, n equals 5/3. Now, was my strategy just then quick and efficient in getting the problem done as quickly as possible? Yep. So is it super dangerous if you were to do that in a test?
Yes.
Just a warning. Because little mistakes, the addition, the subtraction. Hey, summer review corrections. How did that go? I don't know how many times I saw 3 times 3 is 6. I was like, 1, 3 plus 3. But it's going to happen. It's going to happen. You're learning more complicated math stuff, and so the easy stuff is going to be your downfall. So just be careful. Just be careful. All right. I don't remember. Oh no, there was a section like this on homework. It might have been before 62. Sorry. There was like a little awkward section with the square root of 49 minus x squared. Yeah. Sorry, that's okay. This will help. Here's a quick technicality. I wanted to make sure you guys got the big idea of continuity and the big idea of piecewise functions. Ooh, piecewise functions. Interfoldable on limits. There was actually something to do with piecewise functions. Maybe we'll revisit that at the very beginning of class tomorrow. Go back to the limits foldable in our notes and finish up that section. It'll be a good review. So I saved this technicality till a little bit later than the book did. This definition for continuous is our forever card definition. Is a definition that we're going to be using. However, he breaks down, I shouldn't say he breaks down. He gets a little complicated when applied to a closed interval. It gets a little complicated when applied to a closed interval. And so I have an example to show you how it gets complicated and how or why technically they have to kind of rework the definition of continuous for a closed interval. We can't just use the forever card. We have to be a little bit more precise. Kind of like in geometry, there are corollaries to theorems. Corollaries. Kind of like a corollary. We have the big definition. We have the big idea, but this is kind of important at times. The OCD one, I'm sorry, that's spacing. That first guy should be spaced over a little bit, yeah. With each new version of Smart, everything gets off just a little bit. That's better. Still annoying. So if a problem is asking about whether a function is continuous and it includes closed intervals, we just have to rework our understanding a little bit. When you're finished with your example, put your pencil down and have on your fingers what time you went to bed last night. And if you don't have enough fingers, you went to bed too late.
What time you went to bed?
I was watching stuff.
Oh, this is neat.
Hello?
Problem solved.
I went to bed at 8.
Well, at 10. At 10?
At 8? Not even lying.
Oh yeah, Abby goes.
But that's how she's like this.
I didn't work though.
What?
Wait, Abby.
What? I didn't work.
Actually, what time did I go? I don't even remember.
I did not. It hurt me yesterday.
See, I went to bed at 10, but woke up a few times till 11.
Is that 1 or is that 11?
I think I was.
Yeah.
Or no, actually.
When I went to go to bed, I
Alright, I'm actually curious if you are done. What time do you go to bed? 11. Is that normal?
Usually 10 goes out of it.
Oh.
Are you in physics? I heard physics has a lot to do. What, tomorrow? Today? And tomorrow? Nice. When's your first physics test? Have you already had it?
Next week on Thursday and Friday. I mean, Wednesday and Thursday.
Mrs. Lamb and I, we always accidentally coincide and I have no idea why. Okay. So Wednesday and Thursday? Multiple choice now. She does that too, but we have a test next week, so I'll see what I can do. Actually, that's a good thing I asked. And then none of you guys are in AP Chem or AP Bio, so don't worry about that. Although period 6.
I'm bio.
Oh, because there's 2 sections. When's your guys' first test?
Today.
Oh, alright. Because we're next week. Have fun with that. Guys, negative infinity to 2. What would you naturally say now that you have the example written down? Continuous or not continuous? Yeah. Default. Continuous. Totally. Because is there any problem up until here? No. And does it even include here? No. So yeah, totally continuous, totally fine. You know what? We're just gonna circle it and say yes. Okay. My orientation's a little off. How about from 2 to 5?
No.
Actually, no, but sorry, Cheryl.
When you look at it quickly,
How about
a lot of people would say no. Why? Well, there's a break, and there's a break. So no, if you're including 2 and 5, there are issues at 2 and at 5. But hold on, wait. When we're looking at a closed interval, and this partially has to do in homework, I'm just going to show it, you don't have to write it in your notes. In homework, you actually had functions that were asking you about continuity on their domain, that like, if you go beyond -7, it doesn't exist. If you go above 7, it doesn't exist. Like, you can't look any other direction. We can't do this limit from 2 sides of -7 and 7 because -8, -7.1, they're all imaginary. So we have this definition that says when you have a closed interval, you're only needing to come from one side. Now here's the struggle. Did anybody catch my typo? That's bad. We need it to be continuous everywhere in between, and then we need to come look at the interval. This is all the x values from A to B. A is the low number, B is the high number, the far left to the far right. I can come from above A. In this one, I can come from above -7. Those numbers will exist. I can't come from below A. It's not in the interval. It's not being considered. It doesn't matter. This should be B from the left. I apologize. Man, I didn't even catch that typo. I was staring at it for like 5 minutes as you guys wrote. That should be B from the left. Looking at the closed interval, the numbers that are included, A is the low, B is the high. I have the numbers a little bit higher than A, and I have the numbers a little bit below B. So check it. In this one, I'm totally fine. I'm not considering imaginary numbers. I'm not going beyond -7 or above +7. Bless you. However, down here, it's a whole other story. There are things below 2. There are things above 5. But am I supposed to be looking below 2 or above 5? No. So check out, literally, the point at 2 to the point at 5 and everything in between. Is it good?
Yes.
Continuous. But why is this? It's the exact same as this one in that it's totally fine up until, but it's closed instead of open. So where is the point at 5? Not where it should be. So the limit from above this closed interval, I know it's half open, but that just goes forever. The definition of continuous would say, okay, you need to come from above 5. Perfect, the limit exists. You need to go at 5. It's up there. We're still not considering the below. We don't care about this portion of the graph, but we do care that the point is removed. Does it make sense why that one is and that one's not? Because of the bracket and because the point was removed. Now, what if this was a hole and that was filled in? This would have been fine and this would have been failed, right? Because you would have had to, But it's not that way. Let me erase it or else everyone's going to get confused and it's not going to be helpful. Question, Kathleen.
So, one of your examples, like, you have to make sure that the bracket or the parentheses match the whole.
The limit coming from the proper direction as indicated by the interval has to match up with the point when there's a bracket. So the limit from the portion indicated by the interval has to match up with the point. The limit from the direction indicated by the interval has to match up with the point when there's a bracket.
So since it's a whole, it doesn't.
Because the limit would exist. It would be whatever that is, right? From this direction. The limit exists. The point is here. We have that break. We have that not equal to. Hence the discontinuity.
So if it was a parentheses instead, you would
Totally fine. Because then you wouldn't actually be looking at what's there. So. Okay. Now we need to get to IDT. For those of you guys who are in 0 period, I was like, hey, if you're bored, you're totally copying homework. There is a new forever card number 5. I'll need to add it. Oh, I should have done that one time. Just a little bit. Be like, woo. Okay. But the intermediate value theorem, IDT. In calculus, we have a lot of acronyms. We have IDT and MDT. Oh, rules. We have FTC, part 1 and FTC, part 2. Anyway, this is the first. IVT, intermediate value theorem. And the way that I would remember it, even though I wouldn't, unless you want to put it in your forever card, is, I think I made it gray last time, when we were doing like the approaches and the acts, and I was trying to give you little ways of remembering. In between function values exist for continuous functions. In between function values exist for continuous functions. That's basically all of IVT summed up in a little tiny, not very mathematical, but conceptual way. Intermediate, in between. It's not beginning, it's not advanced, right? Intermediate, in between. Value, function values, y values. In between, intermediate, function values, value, yeah. If f is continuous on the closed interval a to b, it needs to be continuous all the way to the end with the points there. That's kind of what you just saw. So to talk about a closed interval, okay, it needs to be continuous. If you were in between and all the way up to and including the endpoints themselves. And if k, my program doesn't like the little element signs, I have to put it in later. You guys see I left little spaces. If k is within f of a and f of b, so it might be helpful for some of you guys to make a note that k is a function value, or k is a y value. If k is in between two y values, he's a y value also. He is the guaranteed in-between function value. But he could be a whole interval, a whole range of numbers. Then there exists at least one number c. Okay, hold on. He's in between x's, so he's an x value. Such that f of c equals k. Oh, it was covering it. Yeah. I just had extra. I can actually move it, but well, now I can't. Okay, this one, yellow box, forever card number 6, I think, right? Because that's forever, no, number 5. Those the answer. Forever card number 5. We're going to include that little final note because IVT, the in-between function value theorem, guarantees the existence of zeros or roots of a function. And we're going to put a little when there is a sign change of a continuous function. If you have a continuous function where there's a sign change, a positive to a negative or a negative to a positive, then we have a guaranteed 0 in between, which is kind of a big deal. But that's not the only thing that's guaranteed. That's not the only thing that's guaranteed. You guys actually saw this last year, the intermediate value theorem, but it wasn't used near as much as it's going to be this year. I'm going to show you like a visual that kind of gives the explanation for what's going on, and then we're going to peek at a homework type problem to make sure you guys know how to apply it after Kyle's question.
So, on the 9th, when we have our forever quiz, we have to quote the definition for like this forever card.
It's a good reminder because you guys should be updating your forever cards and starting to study them if you're not already. I said it briefly the other day. The forever quiz is out of 10 points always. There's always some opportunity for a bonus. And so my people that are strict memorization people, tests will be really hard because problems change for math on tests, right? They're similar, but they're different. But forevers are literally regurgitating information. But how could it look? On forever quizzes, there are problems that are worth half a point, 1 point, or 2 points. Half a point problems could be, and it depends on how long the quiz is and how long class is, etc. I might make a half a point like a 1 point. But in general, 0.5 point, 1 point are going to be short things like state a Pythagorean trig identity. So that's what I'm supposed to give me a sketch for e to the power of x. Make sure you show me the horizontal asymptote, and that it shouldn't cross the x-axis, and have it swoop up, and you're good. Full credit. I show you a sketch of a sinusoidal wave that starts at the top and then goes down, and you identify it as cosine of x. Those are all like 1 point, 0.5 point problems. But then, or I say, give me a special limit, or I give you half of a special limit when the as u goes to 0, sine of u over u, and you have to answer it's 1 or it's 0. Okay, but then I could say for the 2 point problems that are worth like double to quadruple the other problems, state the entire definition of continuous. State all of IPT. Now it's rare that I'm going to do 2 of those because of time, and forever quizzes are always on half sheets of paper until the forever final. Or the large forever quiz. Don't worry, that's later. But those would be examples of ones that I probably wouldn't ask for just like a little detail. Sometimes I do. That one's not a good one. Maybe for definition of continuous, I just say something like, hey, state the 3 conditions that must be true, and you could give me this, or this, or that. But if I say state the entire thing, it means with words. Cool. But then I'm also giving partial credit if you like miss the whole f is continuous, which is key, because if f's not continuous, there's absolutely nothing guaranteed on the chart. But if you don't write if f is continuous, I'd probably just take off like a half point. Maybe a whole point. That's the whole point. But anyway, that's so down here, if you were to do something like, and I just show this to give you, okay, there are lots of letters up here. A and B are x values. F of A and F of B are y values. Now, A is always lower, B is always higher. The y values, I don't know. F of A could have been higher, F of B could have been lower. Who knows? But if I do have a continuous function, A would go with F of A, B would go with F of B. If you're not given any other information, or if you're given a table of random assorted values, let's say you were to give some in between, you were given a table and it was up there, and then it was like here, and then it was like down here. They could ask, okay, well, must it be this value k? And if you have a continuous function, this k will be reached somewhere. Now, just because you're given a table doesn't mean I just get to go like, yay, that's the function. Because it could have kept on going up higher, it could have gone down lower, it could have actually done like some oscillation-y things, who knows? But I can say, okay, I don't know exactly how all these connect, like maybe it went down and then up, maybe it went up and then down. I don't know exactly how these connect, but because I know where it started and I know where it ended, and I know this function is continuous, all of these values, all of them, must be hit at some point within A to B. Maybe once, maybe twice, but this guarantees at least once. Now this might seem kind of silly to you. The example I use in pre-cal, I think I have time, is when I was born. I should actually ask my mom how long I was. I don't remember. I know I was 10, 11 as far as how heavy I was. But, how long was I? Anyway, I was short. I was small, right? And that's like a verifiable. I have like my mom's wristband and my little like whatever it was, and it's in the baby book. Okay, I was small. I promise. Now I'm not. Yeah. Was I ever 4 feet?
Yes.
Oh, 5'2".
Yes.
Oh, 5'3" and 4 and 5 and all of your cute little heights. Just kidding, some of your
I
but
remember that.
was I ever your height?
Yeah, I remember
Yeah.
that.
Why? Because growth or height is a continuous function. To get from here to here, I had to pass through. Now, sometimes it was quickly, sometimes it was slowly, but I had to pass through all of the in-between heights, right? Now, was I ever 7 feet tall? Oh, gosh. Thank the Lord, no. But actually, I had hip surgery that stunted my growth. Go figure. But anyway, coming back. I need to drink coffee. That's supposed to stunt your growth too. Anyway, I don't know. Coming back. I'm not guaranteed to reach 7 feet. Actually, I'm probably guaranteed not to ever reach 7 feet, right? Because it's outside my range, but I was guaranteed to hit all the heights in between. That's what this is talking about. But in math, you have different scenarios besides height. Or maybe 1 second you are higher and 1 second you are lower. So you're like, hey, could you actually have passed through down here? And you're like, well, I don't know. You can only be guaranteed what was in between the beginning y value and the ending y value. So to that end, you might see a question like, I want to see a question. Here we go. Like these. Like these. Now that one has a video. Let's not do number 99. You guys can go watch the video and watch someone else explain it. But number 100, let's play with that one. And this one says, verify. That's an intermediate value theorem. It's not hard. Intermediate, in between, value, y value, in between y value. Exists, or applies, sorry. Then find C. Now hold on, who's C? Is he the X or is he the Y?
X.
Find the X value guaranteed by the theorem which says f of C has to equal K. Okay, so for number 100, what do I need to be true for IDT to apply? Function has to be continuous. Now, my example I just gave you, height, it was super continuous. Let's go into like marble for a second, okay? If I was standing here, and then you guys closed your eyes, started a stopwatch, and then I had you open your eyes, and then I was randomly over there, okay? If marble wasn't true, and all the like sci-fi stuff isn't true, would I have had to have passed through every single location between here and there? Now, could I have been like running back and forth and jumping around and like going all over the place in between? Yeah, I could have passed through it tons of times, or maybe just once. You don't know how I did it. You just know, okay, she had to have passed through all of those. But why am I bringing in like marble or some different sci-fi stuff?
They go in through time.
Because if I could either, go outside of town, or if I could be like transported over there, would I necessarily have been guaranteed to go through? So is it important to know whether or not something is a continuous function? Because if I teleported over there, right? Would I have had to pass through like a minefield or laser beams or whatever? No, you could have like gotten around it and just like, poof, there it is. Anyway, we'll talk about the fourth dimension and how it's time and how maybe Jesus just pops through dimensions when he was going through walls. But that's a whole different discussion for a whole different time. He's still just as powerful, but it's a really cool idea. Anyway, coming back, what happens when you're a math major at a Christian college? Anyway, so X value. We're looking for the X value guaranteed. It is guaranteed because F is continuous. However, that's not the only thing that needs to be guaranteed because check it, I have a Y value that they're looking for. This is K. If you need to like draw it in together with the theorem. 0 is K. 0 is the Y value. Is 0 guaranteed? Yeah, because no, these are X's.
You draw a graph.
Well, you could draw the graph, or couldn't you be super snazzy and check out what is f of A and what is f of B? If this is in between both of those, guaranteed, yes. And we can go find the C that's guaranteed. If I plug in 0, I end up with 8. If I plug in 3, I end up with 9, 17, 18, negative 1. Double check me. Mental mathers, how we doing? Because 9 and 8 is 17, and 17 minus 18 go out of order because I don't like minuses. Negative 1. Is 0 in between negative 1 and 8? Ah! Hey look, a negative to a positive. Of course there has to be a 0 for a continuous function. Sign change. Anyway, we can say f is continuous and f of C, which equals 0, is in between f of A and f of B. Check. Therefore, IDT applies. Without writing a whole paragraph, which probably most like college professors would want me to do. And how do we find the X value? How do we find the C? We say, oh, the theorem says f of C equals K. So f of C would be C squared minus 6C plus 8. Whoa, how did I get that? I plug in C. C is an X value in the function. And what do they want me to set it equal to? 0. At this point, I say no big deal. This is easy factoring with a leading 1 coefficient. So I have a 2 and a 4 and a minus and it equals. C equals. But why am I crossing out for and saying the only guaranteed C is 2?
It's not between X and Y.
IDT is all about in between. 4 is not in between. Forget him. And if 0 wasn't in between, forget that. The whole theorem doesn't apply. Whether or not it's actually true, there was no guaranteed existence. And I believe this is what will get you up through number 102, which is the end of homework. Am I right? ish, sort of, kind of. We skipped a page, but it's not a big deal. If you want to see what I was going to write down, what I was going to have you write down, it's the whole idea of if f is continuous, okay, beginning of IDT, f of A and f of B are non-zero, so they're not zero, they have opposite signs, there exists at least one solution. But didn't we kind of just write that on our little doop for our forever card? Oh, we can't show it on the screen. Sorry. Repeat. I basically said that right here. When there's a sign change of a continuous function, I will have a guaranteed 0. So I don't think we need to take that whole page of notes, unless you guys really want to. And with that, section 1.4, homework number 4, is due to, oh, I can't show you that yet, tomorrow. Today we were supposed to start section 1.5. Wait a minute. Hold on, we've seen this before. I'm saying this because someone asked me this morning, is homework number 5 still due on Friday? Maybe it's going to be due on Monday. Well, have we talked about this guy a little bit?
Yeah.
How about a lot?
Yes.
Ah. So wait a minute, what if there were other infinities, like horizontal asymptotes? Have we talked about them before? But if we're going to infinity, degree test, summer review packet. So come tomorrow ready to review, but get notes down, but I think we'll still have that homework due Friday. You guys know me, I'll be fair. If I don't think it should be due, I won't have it due, but homework number 4 definitely due tomorrow. Bye guys.